And it's my pleasure to introduce Chase Harding. So we're lucky to have Chase here with us today as our presenter. He's a senior energy engineer 5 here at CLEAResult. Chase graduated with a bachelor's and master's of science in mechanical engineering from the University of Arkansas. And he's a professional engineer, a certified energy manager, certified M&V professional, and a Department of Energy Qualified System Specialist, and I could keep going on and on. So, but suffice to say, we're in good hands, and I'm really excited for Chase to guide us through Cost Effectiveness 201. And with that, Chase, let me hand it over to you.
All right, thank you, Nick. I appreciate it. Like Nick said, I am an engineer, and we're going to be talking mostly about finances and my understanding of this is an engineer's understanding. Those of you that have MBAs and other degrees that are better suited to this, I may use a few words that are different than what you're used to, but hopefully I'll get the point across in a a timely and a good and a professional manner. So just going over the agenda real quick. We will do a review of the cost effectiveness 101 session that was presented last year in the same webinar series and was presented last year at Energy Forum. We're going to go through that really quickly. There is a recording of that session that's available for those of you that didn't attend that. If I start talking about some things and you're not sure and you want to go back and review those, the slide deck or the recording that is available and will be made available to you. But I'm going to do a very quick review of the general concepts of what happened in that class. And then we're going to take a deeper dive on some of these financial concepts: discount rate, net present value, lifetime cost and benefits, avoided cost. And then we're actually going to get real nerdy about it, go into my engineer mode, and I'm going to pull up an Excel spreadsheet that has an actual model of what happens with these inputs as we change these inputs. We'll start with a measure, and then we'll go into building a program. How do we, if we have multiple measures that interact with each other inside a program or inside a portfolio, how do we build that to get us the target scores that we need in our cost effectiveness testing. And then we'll have a summary and time for questions at the end. So again, this is the second session in our series of cost effectiveness. 101 was, again, last year on a webinar and at Energy Forum. 201 we presented live at Energy Forum, and 301 is upcoming. But 101 covers the basics. What is a benefit cost ratio? What are the 5 key tests? I'll go over some of that stuff. Now we're going to go into the deeper dive. We're going to model some things like I just said. And then 301, the upcoming session, which will be later this year, sometime next year maybe. We're don't have it actually on the calendar yet, but upcoming will be a lot more in depth, and we'll really start talking about nuance and how these things really affect us as a company and you as a utility. So that's coming. Stay tuned for that. Let's jump into what happened in 101 then. Why do we do cost effectiveness tests? What's the purpose? These tests, and there are several different ones that we'll talk about, but these tests are to give us an understanding of whether our offerings are really beneficial to the impacted stakeholders. And we use that big word stakeholders because there are many different ones, right? We as implementers, you as utilities, the ratepayers, the actual participants, there are different cost effectiveness tests depending on the point of view, depending on who the stakeholders are for that particular test. It's really critical in planning our portfolios, our programs, because we typically have targets that we need to meet, whether it's from our regulators or whether it's a legislated program. We have these things that we're expected to do or maybe required to do in our programs. And using these different tests, we can determine how cost effective we're being. So we want to answer things like, is our offering overall cost effective? Is our whole portfolio cost effective as a group? Is a single measure cost effective as a measure? How do we impact things like rates from ratepayers? How do we impact the finances of the people that actually participate in programs? What kind of adjustments do we need to make if there are measures that we need to include that maybe aren't the best in terms of cost effectiveness, but there are reasons why we need to include those measures in the programs, and we'll talk about that. So again, this came up in 101, and this is the definition, the just basic formula that we're going to use a bunch of times today. This is not a math class. There will be some math, but you don't have to do it. I'll do the math. I've already done the math for you, so don't get your calculators out. But the benefits cost ratio tests, and there are several of them, are all defined as the ratio of the present value of the sum of all the benefits divided by the present value of the sum of all the costs. If the test of result is greater than 1, that means it is cost effective. If it's less than 1, it's not cost effective. If it's exactly 1, then it's a break-even point. And again, depending on the point of view that we're looking at, who the stakeholders are for the specific test, those values can be quite different for one measure. So again, here are the 5 common tests. And I say 5 common tests because there are many territories or different stakeholder groups that may modify some of these tests and may disagree on what the inputs actually should be. So there are a lot of like TRC, there's an MTRC, and there's probably many versions of a modified TRC. But the TRC is the most common one, total resource cost test. This is intended to give a metric of cost effectiveness from the perspective of the service territory as a whole. Will the total cost of energy in the utility service territory decrease because of this program? So it's really about controlling rates. And this is, again, most common because a common reason for these energy efficiency programs is because our regulators are telling us that we need to keep rates low. And of course, energy efficiency is the cheapest fuel. So TRC is the most common measure. It's cheaper to do energy efficiency than it is to build infrastructure, typically. The next one is the properly coined program administrator cost test. I will probably mess up and call it utility cost test, but recognize that it's not just utilities that are implementing these programs. In some states and provinces, these are actually implemented by the state or by the province. These may be a sort of a regional effort that's administered by a group of utilities. So program administrator cost test is the right word to do it. Again, I'll end up probably saying utility cost test, but that's the cost effectiveness for the utility or for the program administrator. Is this good for for us? Will the utility bills, will the utility cost increase or decrease because of this program that we're offering? Next would be the participant cost test. And this is sort of the easiest one because if you participate in these programs, typically you're benefiting from them, right? So the question is, will the participants benefit over the life of the measure? Now that's not to say that's the same thing as will the ratepayers all benefit. And so that's the next test, the ratepayer impact measure. And those two go together because, again, oftentimes in programs, they're ratepayer funded and not all ratepayers will participate. So the participants get the benefit, the ratepayers may or may not. But we have this RIM test to answer that question because there are energy efficiency program designs that allow every ratepayer to benefit whether they participate or not, right? Because we're trying to keep energy costs down. And so they may not get an incentive, but the overall program may keep their rates low and therefore they participate or they benefit even though they don't participate. The last of the 5 is the societal cost test. And this is really an up and coming test. A lot of people that didn't use this a few years ago are beginning to use this. As we go through the politics and talk about cost of carbon and these other things that are happening in our industry now. The societal cost test seems to be being used more and more. These other tests don't include things like cost of carbon typically, but societal cost test includes those things, and also includes things like health and safety, and improved medical outcomes for participants or for ratepayers, really societal things that aren't part of our traditional utility model. So these 5 tests, different perspective. What is the cost effectiveness to the different parties? Not just what's the best for somebody that gets a rebate, but all these different things that give different perspectives for each one of these groups of people. Again, from 101, this slide and the next one, sort of different ways to look at those 5 tests. In this table, we sort of see avoided cost of energy and demand are things that are always a benefit, right? If we save energy, we save money, and we would then expect for those savings to show up as benefits. My pointer is not writing correctly. Let me erase that. Let me not erase that because I can't figure out how. So we would always, in all of these tests, expect to have the savings as a benefit, right? Savings or benefits. We would also expect things like program overhead, utility equipment cost, the actual cost of the products, those things that all end up on the cost side. But then the reason this slide is important, the reason this table is important, is because when we then start talking about incentive payments, that is a benefit to the participant. So it shows up on the benefit side of participant cost test, but it's a cost to the ratepayer and to the utility that are paying out those cash flows. So something that's an input for a benefit in one test could be an input for a cost in a different test, and that's the point of this table. Another way to look at it, this is really kind of the same information packaged a little bit differently, but a table that shows for each of the inputs and then each of the tests along the top, which categories go into either benefit or cost or aren't included in the test. And that's important too, that there are different inputs to the different VCR tests. So not every input is used on every one. So that was a pretty quick, I think, overview of 101. And again, I'll go back and point out 2 things. Number one, the recording of that presentation of the 101 class is available, can be made available to you if you'd like it. And number 2, questions in the chat. Feel free to type things, and Nick is watching those. And if there's something that needs an immediate answer, I'll stop what I'm doing and answer it. But seeing none of those at this point, I will move on to post 101. So again, we got some questions after 101, and then just realized some things that we needed to really kind of get down deeper into, because we're using words that we don't use in the normal course of our regular work days. So we're going to talk about discount rates, net present value, lifetime cost and benefits, and avoided costs. Those 4 sort of concepts. Before we do that, we again have to go back to the basic of what are we talking about in benefit cost ratio test. So we saw this little formula before. BCR is the present value of the sum of all the benefits in terms of dollars divided by the present value of the sum of all the cost in terms of dollars. And many of you have probably heard the term net present value. Whether you know what it is or not, you've at least probably heard the term. And we talk about that in terms of annuities and in terms of investments, in terms of our retirement accounts, those sorts of things. We usually talk about them. We usually talk about net present value in those terms, about how much is an investment worth over its lifetime, right? But we don't, we can say this is the value of our portfolio today, and we can project out what's the value of our portfolio going to be in 5 years, in 10 years, in 20 years. But we're talking about net present value as a value discounted to today's dollar, right? Discounted to today's value. So what is the expected value of the investment that's going to mature in 10 years? What is its value in today's dollars? Because today's dollars are what matters to us today. So we asked the question then, what is the value of a dollar that you don't have yet, but you will receive that dollar in a year? And typically the answer is it's less than $1. Because of inflation, we're all very aware of what's going on with inflation in this country right now. We could say that if we have $1 today, we can buy a certain number of apples with that dollar. And we would expect, because of inflation and other forces, that a year from now, it's likely, not guaranteed, but it's likely that we will buy some different amount of apples with a same dollar bill if we just held on to it and then went to buy apples in a year. So the value of the dollar is decreasing over time, typically. In energy efficiency programs, we're really asking, what is the value of $1 of benefit, right, of the actual savings, if we have an energy efficiency measure that has a estimated useful life of 10 years, right? We're going to save some number of energy. That amount of energy we expect to persist over time. It's going to be the same amount of energy every year for 10 years. What's the value of that savings today? It's whatever it is in today's dollars. But what's that value in 10 years? It's a different number because of the time value of money. We know that we expect that that's going to decrease over time. So we're really trying to answer the question, should I invest this number of dollars to receive this different number of future benefits, right? And energy efficiency, again, it's a savings that happens every year or every billing period, or and it happens over a lifetime of a measure. So two new formulas. Again, you don't have to do math, but we need to be aware of these formulas because we're going to use them several times in the next few slides. So the present value formula, and this form of it is usually used when you're calculating present value of an annuity. So that R, let me actually just go to the next slide, and the formula there is on the top. That R it stands for return. When you're talking about this as an annuity, it's probably more appropriate for us in energy efficiency to talk about that just as the future value, right? It's the return at the sub T, the return at the time. So that's the future value that we're looking for. And then the denominator 1 plus I again in annuities is interest rate. We're going to talk about that as discount rate, and then T is the time on the timeline that we're at. So in year 1, that T is at 1, and year 2, that T is at 2. Same T, top and bottom. But anyway, so in that equation, I is the discount rate. What do I mean discount rate? I just said interest rate. They're a little bit different things. Discount rate is the business's cost of borrowing money, right? It's the cost. It's related to the cost of capital. So, for instance, your bank is offering a loan right now at 7% APR. We can argue about whether 7% is appropriate or not, but just for the point of this conversation, your bank's offering a loan at 7% annual percentage rate. We know that lots of things differ, right? If you're buying a car versus if you're mortgaging a house, those interest rates are going to be different. If you have great credit or bad credit, you're going to get different rates, et cetera, et cetera. We as utilities and as businesses associated with utilities have a much different outlook than I would personally, right? We have lots of things as businesses. We may have a fleet of line trucks, utility, bucket trucks that we have to buy. That's sort of a shorter term thing. We may have power stations that we're investing in that are going to last 30 or 50 or whatever number of years. We may be building solar farms, and we're getting different rates on that, right? We can borrow money at sort of bank rates for some of that stuff. We can issue bonds maybe for infrastructure projects. We can have different sources of funding. There's federal money that's floating around right now. All of these different things that play into your weighted cost of capital calculation. So if you go to your accounting department and say, what's our weighted cost of capital? They probably have a number in mind. Discount rate uses that, right? But it's related to that. But typically, when we're talking about discount rate, it's a little bit higher than our weighted cost of capital, right? We can't really compare apples to apples when we're talking about line trucks versus power stations, or bucket trucks versus pipeline infrastructure projects. Those are different things. So we're not really talking about trying to compare energy efficiency to buying a utility truck that we need to run the business. So the cost of capital, typically considers things like risk and opportunity cost. If I spend this money on an energy efficiency program, then it's not available for me to do this infrastructure project or to buy this bucket truck or whatever it is that I might need that money for. So the cost of capital typically is a little bit higher than, the discount rate is typically a little bit higher than the cost of capital. And so if the bank is giving loans at 7%, we're probably using discount rates that are 7.5 or 8, or maybe it's more than that even because of political situations or whatever those things may be. So it's important to understand that a couple of years ago, we weren't talking about 7%, loans. We were talking about 4% loans. And so at the time, we were looking at discount rates that are around 4.5%. 4.5% to 7% in terms of a discount rate makes a huge difference on the present value of a dollar. And I'm going somewhere with this because the cost, or the question that we get is, our portfolio didn't really change that much, but now all of a sudden it's a lot less cost effective than it was last year, 3 years ago when we did the last planning cycle. What gives? It's important to understand that discount rate. If we go from 4.5% discount rate to 7.5% discount rate, it changes a lot of things. So just as an example, just the present value of a dollar in a year at 7.5% is 93 cents. So if I can get it to right this time. Oop. The present value at the old interest rate, the old discount rate, is 96 cents, right? So 7.5% cost of capital, a value of a dollar in a year is 93 cents. At 4.5% discount rate, it's 96 cents. That's 3% different in rate, 3 cents difference in a dollar. That kind of makes sense. But look out 10 years, because again, energy efficiency, that's what we're doing. Lifetime of the measure, maybe 5 years or 10 or 20 or whatever that number is. You start looking at what's the impact in year 10, and check those guys out. At the higher discount rate, we're talking about 49 cents. At the lower, 2 years ago discount rate, we're talking about 64 cents. So 15 cents different. And that's not 15%, that's 15 cents. That's more like 30% difference, just because we changed the interest rates in the country. And so that's a big deal.
Hey, Chase,
Yep.
We got a question. Does the change in energy rates get incorporated into any of these formulas? So like if it might be 10 cents a kilowatt today, but 12 cents a kilowatt in 5 years?
Yeah, so we're going to talk about that in depth here in about 3 slides. We're going to talk about avoided costs. But that's a great question, and the answer is yes, that affects things too. So in terms of just the discount rate, if everything else stays the same, these are the impacts that we're talking about. But yeah, projected costs and avoided costs are things that we're definitely going to talk about. So another example, you invest $1 today. You hand me a dollar bill today, and I say, I'm going to give you $2 bills back in a year, using these present value, net present value equations. That first term is going to be the dollar that you handed me. That's your cost. So R0 is $1. The benefit is what I'm going to hand you back in 2 years, or in 1 year, I'm going to hand you back $2. So that's R1. That's your benefit. Again, discount rate, today's rate, 7.5%, is pretty close. And then we, again, plug into that PV formula, each of those. You see that then $2 a year from now is not really worth $2, it's worth $1.86. The dollar today is worth $1 today because it's $1 today. So it's worth $1. And then the net present value is the difference between those two, right? You take your benefits, present value of your benefits minus the present value of the cost, $1.86 minus 1, and that gets you the net present value. The gross present value would be $1.86. The net present value would be 86 cents because it's the benefit minus the cost. So that's net present value. Again, more math. Plugging back into that was a one first cost, one result. Now let's look at it in terms of an energy efficiency project that has a 10-year lifespan. And I'm just using 10 because it's an easy round number. But you have to go through that same process for every year in the 10 years. A little bit different scenario here. We're saying we're going to invest $5 in energy efficiency project. It's going to save us $1 a year every year for 10 years. Regardless of that conversation about avoided costs that we're about to have, let's just say that the costs stay the same. We get that $1 benefit every year, and we can see we plug into the actual formulas. This is sort of year 1, 2, 3, 4, 5, 6, 7, 8. All of these are decreasing because our discount rate is 7.5%. And that ends up with a present value of $1 received every year for 10 years at a 7.5% discount rate as $6.86. Plug back into that net present value formula from the middle, 686, that's our benefits. $5 was our cost. We subtract that out. The net present value then is $1.86. Then benefit cost ratio tests. This is not one of the 5 that I talked about a minute ago. This is just a generic BCR. The present value of benefits over the present value of the cost. Plug those numbers in, and then our result from our cost effectiveness test would be 1.372. So there's how we get to the number at the end of whatever test is. So if this was a TRC, then we'd say now our TRC is 1.372. Recognize that it's not a TRC, it's just a generic example. But yeah, so questions about that before I get into avoided cost? Because this comes to the question that Nick asked about what's going on if, in those examples previously we're just saying $1, but and we know how to calculate that stuff now. But energy efficiency savings are not calculated in dollars, right? We calculate those when we do M&V. We get that result in kilowatt hours or therms or gigajoules or those engineering units, and then we convert those to dollars. So again, to the point of the question, how do we get from kWh to units of energy? How do we get from units of energy to units of money? And there's different ways to do it. We could just do that simple, take the bill, look at how many dollars it cost, and look how much energy we used. It was $1,000 bill, and we used 1,000 therms. That's $1 a therm. That's our average cost of energy today. Again, to the point of the question, that's not going to stay the same. We know that's not going to stay the same. So if we're doing a lifetime savings, a lifetime projection, we have to use appropriate cost at the appropriate times, and those are called avoided costs. We call those avoided cost of energy, avoided cost of demand. They can be used in any of those units: kWh, gigajoules, therms, etc., CCF, MMBTU. Those are avoided cost. And you as utilities probably are very well advanced on this stuff, right? You may have different levels of rigor that you put in your utility versus others, but utilities are very good at projecting avoided costs. You know that we have to put in a rate case, or we have to put in a whatever it is, because we're gonna build a power plant, and that takes 6 years, 7, 8 years to get done. We want to do a pipeline project, and that's going to take, regulatory, all sorts of hurdles and get done. But we know what's going on in our grid next year and the year after, and so on and so forth. And many utilities project out for 30 years, and I've seen some that are projecting out for 50 years. And if we're not that sophisticated, at the very least, we have the Energy Information Administration that's doing this for the U.S. government. And so the EIA does, and you can go to eia.gov and pull up this graph that I've got here. They're doing projections up through 2050 right now. So not quite 30 years, but pretty close. And they're saying, we've got sort of an escalation in electric rates. They're projecting right now there's a dip. And honestly, this screenshot was from a few months ago, and they're, they weren't wrong. Gas prices are dropping a little bit right now. And they're expecting that dip to happen over the next several years, and then gas rates start climbing again. That's the EIA, though. That's a government thing, and we got to realize that there's, number one, that's the average for the whole company or for the whole country. That's not, just our service territory. It's not our situation. And also there's some politics involved, potentially, without trying to get into that. But our avoided cost may be very different from that, is the point. That if we're a small utility and we're just buying off the grid, if we're just spot buying from open market, if maybe we are a big utility and we own our own generation assets, we own our own wells and our own transmission pipelines, we own our own all of this stuff, our avoided costs may be quite different from a little municipal electric that's just buying off the grid or just buying on contract from somebody. And so, if I am in that situation, I'm a small municipal, then, a lot of the costs of all of those infrastructure things are built into the contract that I'm paying, but my avoided cost may be significantly different than, a different utility that does the same thing essentially that I do. So the next thing to consider is really, well, how accurate can we be? Again, the utility models, internal utility costing models that I've seen have been very good. The EIA is not horrible. If you're somebody sitting on this call, like, I don't know if I have that, and I don't know if I want to go through all of finding out how my company, does that. I just want a reference model to look at. EIA.gov, if you look at what they projected 20, 30 years ago versus what the costs actually were at the time of this analysis, which was, again, several months ago. But the EIA had projected the price in, I think it was 1993, they had projected the 2023 price, and they were only off, electric price was only off by about 10% for the country. So on average, so, that's pretty decent. Counterpoint to that, the natural gas projection was off by 47%. You could maybe make the argument that 30-year projection only being off by half is not bad, but you could also definitely make the argument that we don't really want to run our business based off of those sort of margins of error. So again, utility models are typically very much more advanced than the EIA models, and a lot more accurate and precise than those. But it does, it goes back to, again, the question. We can't just assume that the average cost today is going to be the same cost for every year of the life of the measure. So hopefully that answers that question. But those were sort of the 4 things that I wanted to dive into on this. And feel free to keep putting questions in the chat about those financial terms. While
hey, Chase,
we do that, I'm dragging
question.
an yeah, go ahead.
So, Florin asks, shouldn't the $1 benefit received each year be discounted as well? After all, it's going to be affected by inflation.
Yeah, and I mean that was what I was trying to convey. Maybe I didn't do a very good job of it, but there's a slide that has the individual year calculations for the $1 benefit um, each year. And let me just see if I can find that. Slide 13. Yeah, yeah. So, oh, I went past it. Slide 14. Yeah. So that to your question, that is exactly what we're trying to do. We're discounting the cost to today's dollars, but there's, that ends up being today's dollar is worth today's dollar. But the benefits every year for 10 years are discounted. And so that, because of inflation, that 7.5% discount rate, is showing that the value of a dollar is coming down each year for 10 years. And that's how we get to the end. So hopefully that answers the question. It's a very good question and exactly right. That's exactly what we do. So modeling a measure. I've lost my Excel spreadsheet. Here we go. There it is. Okay, so like I said at the very beginning, I'm an engineer. I like to see things in Excel. We're going to talk about smart thermostats. In the 101 presentation, we had a very generic hypothetical example. Let's see if we can bring it up here. So this is the slide from 101. Hypothetical simple payback example. We have a contract to install 100 smart thermostats. The program is designed, that's all it's going to do. 100, nice round number, smart thermostats, very common measure. We got some random, they're not really random, but they're hypothetical numbers, and they're big round numbers, 35,000, 15,000, 25,000. All of those were intended to be, again, not random, but definitely arbitrary inputs, because those numbers can be very different in different parts of the country, but they can also be very different depending on your implementation approach. So I've modified that table a little bit, and hopefully you can see all my yellow highlights there of all of the things that actually change. So avoided cost of energy and demand, different for every utility. Again, like we just talked about, if you want to use the EIA numbers, great. But if you're on the East Coast versus the West Coast versus middle of America versus Canada, you're going to have different numbers per kWh. Hawaii, how many of us here are from Hawaii and want to have Hawaii's energy costs versus the Southeast, which has very, very low energy costs. So those are gonna change. Additional resource savings. So if you do a smart thermostat project, you save both electric and gas. Typically, if you're an air-conditioned home with a gas furnace, if it's an all-electric home, of course, you're saving heating and cooling both from the same utility. But if you're doing, for instance, a shower head project or a faucet aerator project, and you're actually saving water to save energy, you save those water costs. And so those additional resource savings would be included in that measure. So for smart thermostats, you're not typically saving water, but you are saving both electric and gas. If you're a dual fuel home, you're definitely saving on heating and cooling. Program overhead, again, that's a number that's it could be variable, but that's built into your program. Right? You pretty much know what that is. So that's a number that is unique to you, but maybe not variable. Utility equipment installation, operating, and maintenance. Just if offering a smart thermostat doesn't affect the number of trucks that you have to have and those sorts of things. So we're going to say that's just zero. I guess we could argue that a little bit, but we're just going to say that's a cost that at least. Customer incremental costs, that actually is not the same, right? A X brand smart thermostat at big box store, we could go out and see what the cost is at, but there are different models maybe, so that could vary by cost. There are also different implementation approaches, which is really what we're going to talk about in the model. The bill savings, that's going to vary. Again, different utilities have different costs and prices and tariffs and rates and et cetera. The incentive payments, we're actually going to vary those things in the demonstration to show that different implementation approaches yield different incentive payments, yield very different numbers. Tax credits, you know, at the time, and I think this is still true, there's not a tax credit for smart thermostat. And then environmental and non-energy benefits, again, different territories may be required to not tell us what the energy savings is, but tell us what the carbon savings is. And different territories may not be allowed to make that argument, right? So it could be a big number, or it could be zero, depending on the regulatory environment and the political environment. So those things can definitely change. Okay, so now my favorite Excel model. This is a live Excel spreadsheet. I can change input values. I will do some of that, but I also laid it out in 5 different rows. And hopefully everybody can see that. Nick, is that zoomed in far enough? Readable and everything?
Well, it's small, but
a bit small. Let's just zoom in so it would all be on one screen. But I'll zoom in a little bit, and then I'll zoom back out once we've kind of gone over what's what. So how's that?
Yeah, that's looking better.
Better. Okay. So again, 100 smart thermostats. That's the goal. I haven't put any other boxes around it yet. But what we do have in the model are 2 different building types: residential approach, residential smart thermostats, or commercial, where we're going to put smart thermostats in small offices. So 2 different building types. We have in the residential category, we have 3 different implementation approaches. The first would just be the traditional, and I'm going to apologize to gas utilities. I'm going to take this from the perspective of an electric utility. We can do this on the gas side for a different thing, but residential smart thermostats, and I'm the electric utility. So in my traditional home energy performance program, my residential portfolio, my typical net to gross ratio is 93%. Smart thermostats, from every TRM you ever find, says the measure life for a smart thermostat is 11 years. We expect that savings to persist for 11 years. So again, it's a residential building. The savings is just based off of the building type, which is based off of other variables, but the savings here for these 3 lines is the same because it's a residential building. Savings energy, savings demand. You'll notice though, because I'm the electric utility, when we start talking about gas savings, the gas numbers are the same for 1 and 3, but they're 0 for 2. And that's because of the implementation approach. So what I've got, again, in line 4, the top line is just a regular old traditional smart thermostat measure. I'm the electric utility. I'm going to claim the electric savings, and I'm going to claim the gas savings as a non-energy benefit. The next one is I'm going to cost share this, right? I'm friends with my gas utility that covers the same service territory. And so we're going to share the cost of this smart thermostat. We're each going to pay for half of it. But that means the electric utility claims the electric savings and the gas utility claims the gas savings. So as the electric utility, I don't get to claim those gas savings anymore. The third one in residential is the DI, or is the point of purchase sales approach, the consumer products approach. I'm just going to rebate this at the big box store, but I'm not going to install it. So the incentives, then again, if this thing costs $175 and I'm the utility that's claiming all the benefits, I'm just going to set my incentive to be equal to the cost of it. And I'm going to pay for 100%. Again, as the electric utility, if I'm cost sharing, I'm only going to claim half of that cost, and I'm going to let the other utility claim the other half of that cost. So my equipment costs are half, so my incentive costs are half, right? They're gonna pay for half of it. I can't claim the full cost. And And then again, in those traditional approaches, I'm going to actually pay to have this thing installed. And if I'm the electric utility claimant all of it, I pay for all of it. If I'm, cost sharing, I pay for just half of it. The benefit cost ratios, right? The cost effectiveness tests are a little bit different in those scenarios. So these are TRC. This is PACT, or again, utility cost test. It actually, in this case, it looks like it's a little bit more cost effective to cost share this with my partner utility, my gas utility. In the point of purchase sale approach, again, this is consumer products. I'm not going to pay for the whole thing. I'm not going to install it. So the equipment cost is still $175, but I'm just going to give a $75 rebate. This is way more common. A lot of you now are only offering maybe $25 rebates, but different incentive numbers. I'm not going to install it. And so now my cost effectiveness goes up, not because the incentive changed, right? So I said this is a live demonstration. If I change this incentive number and I go ahead and pay for the whole cost of the unit, but I don't have to bear the burden of the cost of installation, my TRC is 3.5, where if I do have the cost of installation, it's 2.4. If I only pay the $75 rebate, but still, don't pay for the installation, the TRC number didn't change. The incentive is not a cost or a benefit. It doesn't appear in the TRC calculation. But in the utility cost test, the program administrator cost test, changing that incentive from 75 to 175, right? At 75, it's 5.79 for this scenario. I change it and I pay for 100% of it, it goes down to 2.48. It's much less cost effective for the program administrator to offer higher incentives. Put it back like it was. I'm sure that makes sense, but if there are questions about that, please shout them out. Now, for the commercial version, same kind of thing. We don't have a cost sharing one in here, but we do have, I'm sorry, I'm going to back up, apologize. The other difference between the traditional approach where we install it, we pay for it, we install it, we know it's a utility customer. In that point of purchase implementation approach, we're going to just offer a at their counter rebate at a big box store, and we don't know that every person that walks in there is going to be our customer, right? They may have a meter from a co-op or municipal. They may come out of town and get our rebate, whatever. So we have a lower net to gross ratio. So that also is playing into things. So if we had those same inputs, but we oh no, I've broken it. Well, if we had a higher net to gross ratio, our cost effectiveness test would be better. I think this is a sharing issue because I'm running this Excel locally. It's not responding. I will continue on with the PowerPoint. We have all of these different things. Measure names, the building type, the net to gross ratio, the measure life, EUL, estimated useful life, savings, all of these things. Changing each of those has different effects on different benefit cost ratio tests. And that was the point of the demonstration, that, yeah, as we change things, and hopefully back to the Excel screen, but if I change this to be 100% net to gross before I hit enter, it's 3.54. When I hit enter, the UC utility cost test number goes way up if my net to gross changes. So back to 70, TRC stays the same, but utility cost test goes way down as net to gross goes down. All right, now commercial. Again, building type is a little bit different, so the savings is a little bit different. We're not cost sharing, so all these savings numbers are the same. But in a commercial program, typically we're not just giving a rebate, right? We're giving an incentive, and it's based on the savings. It's 15 cents per kWh or whatever that number may be. And so if we treat this measure the same as any other measure in our portfolio or in our program, it gives us, results that kind of normalize what it's a more apples to apples comparison with every other measure in my mix where I'm given 15 cents a kWh. So if I give 15 cents a kWh for smart thermostat, again, incentive is not an input into TRC, so TRC doesn't care about that, but utility cost test does. The lower my incentive, the better my utility cost test is. If we do this in a direct install approach, it's very much like the traditional residential approach where I'm paying 100% of the cost of the equipment, and I'm also paying to install the equipment. And because the savings are a little bit lower, the TRC is a little bit lower in those two scenarios. So that's the
Hey, Chase.
that's the single measure. Yeah, go ahead.
So is there a reason that incremental costs are not being used versus incentive, or is it labeled differently in this example?
Yeah. So the incremental cost is the equipment cost, right? In new construction programs, for instance, you might have the option to either put in a dumb thermostat or a smart thermostat, right? Just a programmable or a manual mercury switch thermostat, whatever is required by code, or you may have different options. And the difference between the cost of those two things is the incremental cost, right? So if a programmable thermostat costs $25 and a smart thermostat costs $200, then the incremental cost is 200 minus 25, which is 175, which is how we came up with the equipment cost for this measure. But that is intended to represent the incremental cost, and that's a good call out because we don't want to fully burden the program, the costs for the program, the cost for the ratepayer. We don't want it to look like if you build a house, the whole cost of this house is burdened onto the energy efficiency program. That's not it at all. It's only the incremental cost of the efficient equipment, right? If we're paying an incentive on an air conditioner, we know that they were going to have an air conditioner one way or another. The baseline air conditioner is now a 15 SEER, and they're going to put in an 18 SEER. So they're going to, the savings is basically 3 SEER, but that baseline piece of equipment cost $10,000 and the efficient one costs $3,000. We would put in the equipment cost field, we would put that incremental cost, $3,000, not the whole cost of the equipment. Hopefully that answers the question. That is what that is intended to represent, though. Okay, we only have a few minutes left, and I do want to leave some time for questions. This is the same 5 lines from the single measure. I've just zeroed out all of the approaches again. Remember, our goal was just to install 100 smart thermostats. So we've got 100 smart thermostats in there. We've got a whole bunch of other measures, and just for round numbers, these are all actually the same measure. But they could be whatever you wanted them to be. And the point here is that we have this thing at the bottom that's called necessary measure. A necessary measure may be something like I just described, incentivizing an air conditioner. The baselines keep going up. The federal baseline is very, very high. The savings is very, very small. The incremental cost may be high compared to the savings. So cost effectiveness wise, it's not very cost effective. 0.36 is not far off from what a air conditioner incentive looks like. But we have to have that in our program. It's been in our program forever. Back when the baselines were low, or there were no baselines, before 2007, our program was really built on air conditioner incentives, and so it's just baked in. We have to do it politically. We can't take that measure out, but the TRC is low, right? The cost effectiveness is not good for that measure. How do we fix that? And we do things like we change the weight so that that measure is less of an impact on the portfolio, and this measure that has a very good TRC score, or all of these measures that end up having a good TRC score, balances out the portfolio TRC, so that we get an overall, an average of these numbers that that comes out to, in this case, 1.21, where if we don't do enough of those measures and we do way too many of these measures, this average ends up being much lower, 1.16. If we did nothing but poor cost effective things, then this isn't the weighted average anymore. I broke it, sorry. Hopefully you can see the point. I just realized my math mistake there. As I change those, it changes the weightings of everything. But as we put in more measures that are not cost effective, it drags our portfolio level TRC down, or any of the cost tests. And as we do more of the ones that are more cost effectiveness, we can raise those overall scores. So that was really the point of that second model, that we can play around with how we approach measures to do things that are more or less cost effective. We can play with the mix of our measures to get the overall portfolio in good shape. So those portfolio level things, I've only got a couple slides here. Regulators require the programs to be cost effective. There are often these measures that we need to include regardless, so we have to balance the portfolio. Here are a few, and again, we're about to run out of time, but HVAC measures are a good example. This is very slow changing slides. Insulation, attic insulation can be very good, while wall insulation is very bad. Water heaters are bad, or not cost effective, or not very cost effective. And then health and safety measures, I did want to say that we're oftentimes are forced to include health and safety measures, and they don't have any energy benefits, so it's hard to quantify those if we're not allowed to use things like societal cost tests. So in summary, we went over the 5 different BCRs, benefit cost ratio tests. If it's greater than 1, it's good. If it's less than 1, it's bad. We went over all those economics terms. We played a little bit with the 2 models, and then we ran out of time. There's way more of this that we can talk about. I'd love to see everybody at Energy Forum, and we can talk in more detail. The 301 classes will be upcoming, and with that, we'll see if there's anybody that wants to stick around for questions. I want to be respectful of y'all's time, but I am here available to answer questions if anyone has questions they'd like to stick around and ask.
Yeah, so that's our time for today. So if you need to drop, thank you for joining us. Like Jay said, he's more than happy to stay on a few more minutes if you have more questions. And so go ahead and type those into the chat if you would like to stay on a little longer. And next month we have coming up Filling the Lighting Gap. So on May 23rd. So keep an eye on your inboxes for an invite to that. That's the next step in our Learning Series webinars.
Go back to the question slide, but those of you that need to drop, feel free, and thank you for coming.
Okay, Chase, maybe you could review that summary slide again while people type in any lingering questions.
Yeah, so again, we went over a little bit of what was in 101. We talked about the different benefit cost ratio tests, and for any of those tests, scores over 1 are good or cost effective. Scores less than 1 are not cost effective, and made the point that the portfolio, the program, the overall score should be cost effective, but to the last few minutes there, we sometimes include things that are not cost effective and have to balance that out with the rest of the portfolio to make the portfolio cost effective. We talked about discount rate, present value, net present value, avoided costs, there's different things in the economics sort of section. In the measure model, we mentioned net to gross, and that as net to gross ratios are higher, that's obviously better for cost effectiveness. Longer measure lives have larger lifetime savings. I think that's just something that's obvious. I don't think I mentioned that during the slide, but if we do measures that have very short estimated useful lives, then it's hard to get a high cost effectiveness score. Made the point that incentive doesn't affect TRC. Incentive is not an input for TRC, which again is the most common cost effectiveness test. And we talked about several different delivery methods that could impact our scores. That if we pay for the whole cost of the product or the incremental cost of the product plus the installation, then our scores aren't going to be as good as if we just do a at the register rebate. Cost sharing with our other utility could affect those scores as well. And then we just briefly brought up the program model and talked about including those low score measures in a larger portfolio and having to balance those out to make sure that the portfolio is good.
Hey Chase, so how in that example Excel sheet that you were showing, how were you calculating your TRC there versus the BCR?
So let me refer back to one of the 101 slides. And sorry if this is slow clicking through things. Almost there. So TRC, again, it's a benefit cost ratio. It uses, I'm going to go to the next slide. I didn't draw all over. Okay, so in TRC, the benefits that we're using are the avoided energy and demand related costs. So we're calculating the savings in terms of kWh, kW, and therms. And then we're using the avoided cost tables for the 30-year projection of each of those for the next 11 years and saying this is the avoided cost of energy for each year in those 11 years. We're calculating the net present value. I'm sorry, we're calculating the present value of each of those benefit numbers from the savings. And then we're summing those together to get the present value of the benefit of the avoided energy and demand related costs. So that's number one. There's 6 things here. We're doing the same thing on additional resource savings, which again for this measure, smart thermostats, there are not any water savings. There's not any diesel or propane savings. There's not those sort of additional resource savings. But we are, as the electric utility in that example, if we're claiming all of the savings, we're claiming kWh, kW, and therms, then we'll include the kWh and kW as avoided energy and demand costs, and we'll include the natural gas savings and therms as an additional resource savings. And then in terms of environmental and non-energy benefits, we did not claim those in this example. And just to make the point that if you are in other territories, you will either be required to claim those or you will be not allowed to claim those. So that's why there's an asterisk by the benefit number there. But we took those 3 things and calculated the present value and then summed those all together to get the numerator of the equation. So that's the sum of the present value of all the benefits. And then we took the incremental equipment cost, the installation cost, which again in different scenarios we had or we didn't have, equipment and O&M stuff, it's a one-time thing. So in this case, it's just the $175 incremental cost for the thermostat. I think I had $79 in there for installation. Calculated the present value of those, which they happen today. They happen at time 0, so they're whatever the number is. And then you may have noticed at the very end there, when I was changing those quantities on the non-beneficial measure, the TRC score was actually changing just from changing quantities, and that's because the program overhead costs are fixed. And so they're just in there as a static number. So as I change the quantity, those overhead costs get distributed to all of the measures, or really all of the energy savings equally. And so that's why those change just a little bit. But anyway, those costs, the cost of the equipment, the cost of installation, in this case, no additional ongoing O&M costs, and then the program overhead cost are all present value calculated for each of those individually. They're all summed together, and that goes in the denominator of the equation. And then all of those sum of the benefits, all of those sum of the costs divided gives you TRC. That's what we're doing. Hopefully I said all of that right. And if you would like that written down, I'd be happy to do it.
All right. Well, thanks so much, everyone who attended today, and thank you so much, Chase. Wonderful having everyone here and learning about cost effectiveness some more. So with everyone,
Sorry, I was a little bit long.
Have an excellent rest of your day, and we'll see you again. Thank you.